John Davis, who is now retired, at the same place. And I met him as a graduate student still. So if you see him around, say say hi for me. All right, so he's going to be talking about tuning spin photon coupling through polarized cavity states. All right.
Okay, yes, sorry. I was just told how to operate it, and I immediately forgot the information that I was told. But first of all, thank you very much for the invitation. It's great to be here. It's great to be in Natal, and it's great to be in my state, because I'm actually from here. But since I think, well, I don't know how many people know a lot about Glasgow, about what we do there. So I think I'll do some things slightly different from what you saw in the first presentation and give you a little bit of an introduction to both where we are with respect to location, facilities, and research in quantum technologies, and then go on to what we do in terms of research, if that sounds okay. And then at any point, please do stop and feel free to ask any questions. So Glasgow in the UK is the fourth university in the English-speaking world, is the very north of the UK in Scotland, in the west coast of Scotland. And there is a long history of great science that has happened at Glasgow. Most recently, we had the contribution from Professor Sheelan Rowan, who led the group from Glasgow in the discovery, or contributed to the discovery of gravitational waves. But if you look quite far back, you see that Glasgow was actually the home of Lord Kelvin. So that is great for physicists as a fact, which my fact for non-physicists and in the room might be lost to some extent, because people might know this, is that Lord Kelvin wasn't actually known, his name wasn't Kelvin, was William Thomson, and when he was bestowed the lordship, he was asked what he wanted to be called the Lord of, and then he said Kelvin, because that was the river that he looked over from his lab, which was right here, and we have the River Kelvin at the University of Glasgow that goes across the university. So in Glasgow, everything is named Kelvin, Kelvin building, Kelvin galleries, whatever, and everybody just think is because Lord Kelvin, but it's actually not. He was the one that chose it because of Glasgow. And people in the city have a great appreciation for Lord Kelvin in the university. In the park here, there's a massive statue of Lord Kelvin, which people very often will put traffic cones in his head. So that happens pretty much on a weekly basis. As a place to do research in quantum technology, the UK in particular in Glasgow is quite well placed at the moment, because we have a national quantum strategy since 2010. And in Glasgow specifically, this strategy has now given us 2 of the national hubs, so one in position, timing and navigation, and another one in sensor and timing as well. So anything that is quantum or quantum adjacent that can contribute to quantum technologies, that can be linked to one of these hubs is quite well placed. And as I said, there are 4 hubs, 2 of them are in Glasgow, so it's a great place to do that. Now, in terms of research, I know this is about quantum magnonics, and I'll get to magnonics in a second. But I thought before I get there, I'll just give you an overview of what we do at my group in a couple of different topics, just a few slides, and essentially tells you how we got to magnonics, specifically to cavity magnonics. So the first thing, and you will see that people, if you look at some of the literature in magnonics, people have started calling specifically the devices that people make with them metamaterials. And to me, when you talk about metamaterials, it goes back to these artificial structures which people realized in the early 2000s, but that go back to the 70s and 60s, where Russian physicist proposed a material that would have split ring resonators that would give you negative permeability and a circuit board that would give you negative permittivity. And if you combine those 2 things together, you would get something called negative refraction. At the time, people were like, oh, great, excellent, something theoretical that we'll never be able to achieve. And then in the early 2000s, nanotechnology has then enabled us to make these things, and then this is now possible. And then we got things such as super lenses and even invisibility cloaks, because if you can bend light in all sorts of ways, you can actually make light go through or go around matter. Now, if you can do that, so you can get invisibility. Now, these has become even more interesting with the advent of these two-dimensional materials, because you can realize very similar properties just based on polaritons. Okay? And these could be any type of polaritons, excitons, plasmons, anything. You will get them. Particularly interesting in these two-dimensional materials, because when you combine them, you have these highly directional, very low loss polaritons that will travel very far. Now, with that, it comes a lot of applications from detecting and sensing, because they are very sensitive to various things. They travel very far frequencies, spectrometers on chip, subdiffractional imaging, and etc. Right? And what we've done very recently with anisotropic materials like this is actually develop filters based on liquid crystals that you can image biological molecules. And I think here there would be a video that which I think is playing, and you can see just a little tiny bit of motion on a biological molecule. Right? These things are very interesting because they've, depending on the resonance that you choose, for example, plasmons are there from the infrared to the near infrared, excitons would be from the mid-near infrared to visible, and then phonons in that range as well. And then if you want to go very far in the microwaves, you now have magnons, which is where I've done a lot of the work on these particular things. That was quite nice and interesting, and some people thought that was interesting in the OSA and gave us a cover in 2020. And then there is the magnetism side. So that was more of the polaritons. And then in magnetism, we have heard a lot about the applications of magnetism and the basis of that in the first excellent talk. So my interest in particular for this was how to design magnetic phenomena, and started all with something called artificial spin ices. These artificial spin ices are essentially, they were originally designed to realize the behavior that you would get in actual spin ices, but in 2 dimensions. And then people realized, oh yes, we can do this, but we can also do other things that you can't do with anything. We can just design any geometry that we want by tiling these tiny little magnetic moments, and we get all sorts of behavior. Pretty much like a magnetic Lego, because you can control the geometry in any way that you want. And with that, we were particularly interested in controlling spin wave propagation. Now, one thing that came out of trying to control spin wave propagation was we stripped this all back and thought, well, let's look at how spin waves propagate in matter. And what really dominates some of this behavior is magnetic exchange, right? So very recently, or a few years ago, people were doing this thing where they were controlling exchange in a material by growing it layer by layer and then doping it with different things. So you'd get an exchange gradient. You wouldn't have just a single value for exchange across the material. So we looked into this to see what it does, and then you would have a side of your material that had low exchange, a side of your material that had higher exchange, and what happens is if you send a spin wave from one side and then send it from another, you get something completely different. In this case, we're particularly interested in non-reciprocity, which was also mentioned earlier. And you can see that in one side you have really efficient transfer of information, whereas in this side you don't have nearly as efficient. In fact, it's nothing. This is an artifact of the system. Right? This is particularly interesting because it's very similar to what you'd get in systems with Giloziski-Maria interaction without actually having to create a structure to do that. It's just essentially a single film, although there is doping throughout. And then you could make these signal processing devices for directional propagation. Now, and then that came the combination of these things together, and this has already appeared here once, which is, let's put a magnetic material inside of, or this is what people were doing, this wasn't me, but that is the overlap of these 2 different areas of interest. If you put a magnetic material inside of a microwave resonator, which has electromagnetic waves, then you get coupling. And this is quite different from what you get from one of the different systems, one of the single systems in its own. For example, if you have just the microwave resonator, it has a resonance associated to these fields, which is this diagram here, or this plot here. And that just depends on the geometry of the system, right? So if you make it bigger, your resonance is lower. If you make it smaller, your resonance is higher. But there is nothing else really to this. If you take the magnetic material, then if you think of a macro spin, which is a very good approximation for YIG, for example, all you have is an increase in resonance with the magnetic field. And these two things are not necessarily connected. For example, if you just have a cavity box or a microwave resonator, which is just a copper box, and you apply a magnetic field to it, nothing will happen to the resonance frequency really, because there is no interaction there. But now when you put those two things together, you put your magnetic sample inside of your magnetic resonator, then instead of having two distinct resonance frequencies, you have this anti-crossing between those two resonances. And the distance between those two lines here in the middle is what we call the coupling, right, between those two systems. And that is because essentially you are driving magnetization precession with your electromagnetic fields, which is then responding back to the cavity, and there is some exchange of information. If you are driving them independently, this doesn't happen, but when you put them together, then some of your energy that would go into driving the cavity resonance would then be transferred into driving the system and back and forth, okay? Now, since I am the first person speaking, and for the benefit of people who might not be in this area, I thought I'll give you some very crude analogies to what I think this might be akin to in other systems. And please don't judge me if you think that they are completely inaccurate, but I think they've helped me visualize what they are. So the hybridization, if you think about in chemistry, if you think about orbitals, right, we have, for example, S and P orbitals, and we know from quantum mechanics that they have different shapes. When they hybridize, essentially what happens is that you get shapes that are a mixture of both of these orbitals that hybridized in some way, or some shape or form. Right. In a basic physics example, you could think of this, or that is how people started thinking about this hybridized systems mathematically, as you have two springs, and if you go back to physics 1, they're completely disconnected. You can write equations of motions for each one of them. There is nothing that connects them. And what you get is something very similar to what I was talking about. If you change one of these constants, you have one of the resonance frequencies that change with these constants, the other one that doesn't, because they are completely disconnected. Now, you've put a spring in between them, you connected those two systems, this spring constant is different from the others, and now your equations of motions have some terms that connect those two things. And what that does to your systems, you no longer have two distinct resonance frequencies. You have something, this anti-crossing, which is determined by the spring constant on the middle here that is connecting those two systems. Now back to the chemistry example, what I think of when I look at this is, if you thought about these two things as the most basic way of describing those orbital hybridizations, you would start, what this is telling me is that you would start right here with one type of system, and you went up here with another, and the same thing here. When usually you wouldn't have that, you would go all the way with just one behavior or another. So some exchange of information has happened. And that's typically what I'd like to think of when I think of the magnetic photonic system. Why are we interested in this? Why are people generally interested in this? So this was mentioned briefly. I don't remember if it was in the same context earlier, in terms of transduction from microwave into optical frequencies. Because, for example, magnetic materials are well known for rotating polarization. So if you shine a laser onto a magnetic sample, that polarization will rotate ever so slightly due to a Faraday effect, just because of the magnetization, the sense of rotation. If you put this magnetic sample inside of a microwave resonator and the sample is now coupled to microwaves, then whatever comes out of the other side and whatever the rotation is might give you some information about the coupling between the sample and the microwaves. So if you were trying to get some information out of your microwaves with an optical signal, this could be something or a way to do it. Or that was at least the first proposal of what a transducer could look like from microwaves to optics for this type of systems. And this is particularly interesting because if you put a superconducting qubit inside of a microwave resonator and you put a magnetic sample inside as well, those two things will be connected through the electromagnetic waves inside. Okay? So then if you could measure the optical response of a magnetic sample through a laser in the system, this could be very beneficial because the response of a superconducting qubit is in the microwave range, but you also need it to be at superconducting temperatures, which you need a dilution refrigerator, which is quite big and cumbersome. So you need to actually take that information out somehow. So this was what was expected. That could be an application of this. And then very recently, people talked about using just this coupling as a way to do more precise sensing by doing essentially doing these types of measurements at very low temperatures in the millikelvin. So you're working with single photons, single magnons, and then you can have them entangled, and they are very highly sensitive. Okay.
A quick question.
Yep.
I'm also interested in this quantum measurement type things. Are these non-demolition type measurements on the qubit? If you use, a dispersive, coupling to the cavity and you measure something on the cavity, can you tell what the state of the qubit is without collapsing its wave function?
So I don't believe so, because that's not our work, but I don't believe that's what they've done. So I think you have, in this particular case, you are destructing your state, essentially.
Okay.
Yeah.
You need to, just projective measurements. Yeah, that project. Yeah, but there are different types. There are direct and indirect projective measurements. I'm talking about the indirect projective measurements, where you measuring a small system so you can get information from a larger one. Anyway, we have time to discuss later on. Thank you.
So in this case, I think that is a good, to me, that is the idea of what you would, not specifically to this case, but in this case, you were trying to do, I believe, an indirect measurement on the magnetic sample to measure some response from the qubit. So this is where I think people are interested in, where there is a lot of work done on cavity magnonics. But to me, actually, when you think about this, and you have already seen some of this in a paper that came up in an earlier talk, and some of the classical literature, because most of those things that I was talking about was actually what people used to measure the first, were essentially the first experiments to measure ferromagnetic resonances, right? Because you were just putting a magnetic sample into a microwave resonator and measuring the output, right? You weren't interested in the coupling. You were actually measuring as a function of magnetic field and just looking at response to see where it peaked or not, and you measured an actual susceptibility and was related to loss, but the experiment was actually very similar. So, and that is, what we know from Kittel's work on magnetic dynamics. And then these new works are really trying to use this or something very similar to work on this coupling, or to get some information out of the coupling to some extent. But then there were the initial works on this field were trying to describe the coupling using, for example, oscillator models very similar to what I was describing in the analogy, to get some sort of outputs that would fit the data and would give you a measure of the coupling. And this is quite efficient if you have some measure for the coupling and if you have some measurements. The issue here was, at the time, people were not particularly interested or considering, or they were, but not particularly in a robust way, considering the effects of polarization. So for example, you would just say your magnetic precession is driven at the maximum because we know that there is some sort of polarization associated to magnetic precession. This was part of Kittel's work of saying if you have your magnetic susceptibility will peak if you have precession in the same direction as whatever the microwave radiation is that is coupling with it. So they have to both be in the same direction. If you have one right circularly polarized, the other one left, you don't get coupling. Right? So, but people are saying, well, you get the maximum coupling when you are at that polarization, and you get a bunch of stuff with that. And that was great to fit data. But that actually didn't take into account the fact that in your resonator, your microwave resonator, and people had done this before, you need to control the polarization, or the polarization can be controlled. And in most cases, it's not circularly polarized, it's linearly polarized. Right? And the way that people did this to get susceptibilities was using something called electromagnetic perturbation theory, which is just saying you have an empty, you write Maxwell's equations with the empty cavity. By the way, there is nothing quantum about this, and I'll answer the question that came up earlier, if that comes up here. This is just Maxwell's equations for waves. You write it in the empty cavity, and then you write it at the sample. The sample has to be very small, so it's not perturbing the system a lot. And then you get a shift in your resonance frequency, which is dependent on whatever the sample contribution is. And this will change depending on the polarization of the system, because if you have waves into particular directions, whether they are polarized or not, they will interact with the magnetic susceptibility in different ways. So if you have your susceptibility, which is a tensor, and you have a field which you are coupling with that is only, let's say, in the x direction, you are only going to couple to one of these components. If your field is circularly polarized, you are coupling with all components, and that would then give you some polarization information. So that was one of the first things that we thought, okay, this is something that we can look into from a classical point of view and see what we can do with it. So I'll just put here a bunch of people that at one point or another worked on this. So me and my colleague Martin Viders at Glasgow, at the time he was at KIT, started working on this, and then just a bunch of people from all over started joining in, and it was great. It became a really nice collaboration with a lot of funding from also various different places. And the reason why we started doing this at Glasgow, in addition to the things that that I was talking about earlier, is that Glasgow, so we are within the quantum circuits group, and there is something there called the James Watt Nanofabrication Center. And this is a big center for one of the biggest clean rooms in Europe, and you can make various different things, mostly semiconductors, but at the moment, people are really focused in superconducting structures, and in particular, superconducting qubits. So working on magnonics, there is room there, and a lot of people working also on superconductors, and there is a lot of the skills and facilities for microwave testing and analysis that is going on there. And at the moment, a lot of the things that I would just mention, they'll talk about work of Alban mostly, who's a PhD student there, and with Martin and Rory, and then working with a couple of people, Dimitri Bosco in Colorado, and Benedetta Flipus and Jay Nair in Boston College. So we started off with just looking at this perturbation theory and applying or thinking of it as being linearly polarized. You still drive magnetization. You can derive a coupling out of this. It's just not as strong as people assumed it would be, because you are still driving magnetization, but not in that circularly polarized regime. And that's because, as I said, most of these resonators only have these fields that oscillate in one direction. Right? And then we showed that you can control, just by moving the sample around, you could control this coupling quite nicely by having it from going very strong to not quite strong, by just shifting the sample from a place where your field was quite strong to a place where the field was not strong enough. But this is really just a dependence on the intensity with respect to how efficiently you can drive magnetization, and nothing else really. And that was worked quite nicely. And essentially what we're trying to say is that, this comes from, in the macroscopic case at least, this is a purely electromagnetic phenomena, and is just controlled by the type of polarization and intensity of the light. And that works quite well for various systems. You can then change, instead of just having a macrospin, you can have a magnetic, a block or a film, and that just changes the susceptibility that you put in. And the interesting thing about this is that it doesn't matter where you put it in. If you can describe the fields from your resonator into intensity and direction, you can put that into that electromagnetic perturbation theory from the 70s and 80s, and get couplings that are extremely accurate compared to experimental data. So this was something that we've done with actual a superconducting resonator at millikelvin temperature and just a piece of YIG that was put on top, and used perturbation theory to fit it, and that worked quite nicely. And then the idea here and the direction where people were going is we don't want to be able to just be able to describe it or to just understand it. To actually do anything useful with these, especially if you want to couple to third parties, such as superconducting qubit or any kind of qubit, we need to be able to control the coupling, or it would be good to be able to control the coupling. And some of the first things that people were doing in this field was, for example, having either standalone suggestions of what you could apply this or make an application out of this. For example, there was memories based on multiple YIG spheres together inside of a microwave resonator, and you were really talking about how putting these samples in different places or coupling to different or putting the samples at different locations of the field inside the cavity, you can control the coupling between them, or just designing different resonators to actually control the coupling. And is really, there was a lot of work being done on designing the coupling for one way or another. So we got back to this question of, well, how about this? We have shown that we have these linearly polarized resonators. So there is really a factor here which this coupling should be smaller than what we are saying that it is, or people are saying that it is. But how about the circular polarization element of it? Can we create something that reproduces the left circular polarization to right circular polarization element of original ferromagnetic behavior into cavity magnonics? And essentially just take this susceptibility. If you have, what that means is this, you are taking this susceptibility, or the four components of it, and you write them as left circular or right circular polarized. If they are circularly polarized, you get a peak on the susceptibility. If they're not, if they're left circular polarized, you don't get anything. How does that translate to cavity magnonics? It's quite, should be quite obvious to, it was quite obvious to us at least, is that if you have a peak, that should be strong coupling. If you don't get anything, you don't get coupling. But there should be an element of controlling or controllability in between. So we designed a microwave resonator, which was very similar to all of these others in that it is rectangular, but we added two different ports. So in one port, we have just a signal, and then in the second port, we have the same signal, but it drives a field which is orthogonal to the first one. However, we can control this. So when you combine them, as you can expect, if the field is in this direction, the next field is in 90 degrees rotated. When they are both combined, you have a field which is at 45 degrees. There is nothing more than just vectors. However, if we control the polarization of one of these and the intensity as well, we can make any kind of polarization state we want, right? Because we can have two fields that are in out of phase, in phase, etc. So we can go from linear to circular to elliptical polarized with quite a precise degree of control in the system. Yep. They should be in order for this to work. Yes. The error bar is geometric if you were talking about just the modes, because you can machine them quite nicely. They really are orthogonal. And when we put the samples in, they mostly are. But the samples, if the samples are big, they can interact with them differently and they become non-degenerate, yes.
Okay, thank you.
So when you put a sample in, and then as of no surprise, if you are driving with a right circular polarization with respect to magnetization precession, you get very nice strong coupling. If you're driving with left circular polarization with respect to precession, you get no coupling at all. And if you look at how those frequencies or the frequency shift works with respect to the fields, then literally all you get is something that is very analogous to ferromagnetic resonance, where you either have you adding these frequencies or you're subtracting them, and you either get a zero at the bottom or not. So with this, then we tested for, essentially non-reciprocity. So what if we flip the field? So if you are in this particular geometry here, for example, we define left and right circular polarization with respect to some axes. So we are saying that this is right circular polarization with respect to the magnetic field pointing in the plus Z direction. But if we reverse the field, then this now becomes left circular polarization with respect to the magnetization precession, which would now be precessing in the opposite direction. So if we do that, which is simple enough to do in the experiment, then you get, for the same field, but just flipping it, you either get coupling, or very strong coupling, or no coupling at all. So there is a very nice degree of controllability in just reversing the direction of the field. And then you can see here how this mode, or the absence of a mode at left circular polarization is complete. There is no even any trace of it. Okay. Now, if we are doing this, so when we control the field here, we don't necessarily just control it between left and circular polarization. We can control the phases, or the relative phase between them, but we can also control the amplitude. So we can make any phase that we want. So if we just look at a scan on 360-degree phase, but we keep the amplitudes the same, what we get is that we go through here is that first case of left circular polarization, where you have no coupling. Here is where you have strong coupling, but then you also have the coupling which decreases and increases as you go around the phase. And then if you now add amplitude into this, so then we start getting phase maps which look like this, or phase and amplitude maps, where you see again here you have your right circular polarization, your left circular polarization for the same amplitude, but if your amplitudes are different, then you have these elliptical polarization states, which then mean that you have different couplings. So the heat map at the bottom is the measurement, and it's just the intensity of the coupling strength. So it's 0 if you are in the opposite direction to precession, and well, very bright if you are in the same direction. Okay. So that was quite interesting in the sense of, okay, we have now a degree of controllability of the coupling by just either tuning the cavity or changing the direction of the magnetic field. And there was a couple of other works that people were doing with this in different resonators and using different things. For example, one of our students called Isabella Baventer was using a loop with around the sample. So you have an actual oscillating field at the sample location. And I believe something very recent to this has been used last year or this year to obtain something called level attraction in these systems, which is something that I'll not touch here, but it's a very versatile system. And the only reason why I'm bringing it up is what we did with this was a different setup to look at time. What happens to the systems when you don't have a spectroscopic measurement like these ones, but you actually are giving very short pulses. So you essentially give a pulse at the magnetic sample or to the cavity for a very short period of time, or both of them at the same time, and we look at what happened. And here, sort of related to that question that we had earlier on these being degenerate, this is quite different, and I'll just mention this as a case of curiosity. And as I said, Isabella has been looking at this, is the systems are no longer degenerate, and it's quite difficult to control them. So you get these things called level attraction instead of repulsion, because you get interference between these two modes and this back and forth that is quite different from what I'm talking about here. So it's important that they are degenerate for pretty much everything that I'm talking about here. So yeah, we looked at time. So what happens when you use the same sort of phase or phase and amplitude control, but you are looking at this in time? So if you're just driving your system, you have your regular level attraction here, and this is for this right circular polarized, so you have maximum coupling, and you just drive it. What you get is these things that are analogous to Rabi oscillations. They are not quite Rabi oscillations because we are not quantum spins, but they are just this beat of your magnetic resonance, of your coupling between your magnon and cavity photons. Now, if you flip your phase and you have a left circular polarized system, then you completely destroy this. So you have nothing at that resonance frequency. So again, you can go from controlling this both spectroscopically and in time. But then you can do quite interesting things with this, which is, as I said, this is just a short pulse and you look what happens just at one, either with one phase or another. But we can control, because we have these two modes, one coming in this case from the strip line, one coming from the cavity, and we can control them both with different times. So here, if we actually do, this is the pulse sequence. So if we drive the cavity, so we ring the cavity about 20 nanoseconds, and that's all, and then we ring the magnon with this out of phase mode, then nothing happens, which is similar to what we have here. And then immediately we apply a second pulse, which is at this different phase, then we now see these oscillations back again. And then if we apply a third pulse, which is back to the same phase that we had here, then we destroy that, and there's back to no coupling. So this is now us moving into looking at things that are closer, especially if you're trying to couple to these other systems. Having some control or being able to control these things in time is particularly useful. So in terms of these other things that we are trying to emulate or to go, so most of this, which was also mentioned earlier, is done, a lot of this work is really looking at superconducting resonators or superconducting circuits. And these are just very small microwave strips, which are typically made of superconducting materials, so that they can couple, or they are the basis for a superconducting qubit. And then you put your magnetic sample, or really any qubit that you were trying. In this case, it's not a magnetic one, but it's a very similar method of how you measure your magnetic response. So we, at Glasgow as well, we have something called the Kelvin nanocharacter. Oh, yeah. Yep.
The previous one, sorry. Yeah.
Yeah.
So the width of the pulse is the same, should be the same. How much you can play with that?
So the first one is 20 nanoseconds for both of them. The second one is a 20 nanosecond pulse, and then this one is not. I believe is 10.
Yeah, but you can drive these two different states by the length of the pulse, or that's the part that I think I didn't get.
So the length is, it is important in the sense if your length is too long, then you have decoherence. Okay. If you think about coherence and decoherence in that sense, it's classical here. But if you think about decoherence, if your length is too long, then you are back to some sort of almost spectroscopical regime where you are not actually driving these type of oscillations, because your system is almost driven continuously. So you end up getting interferences. So you want your pulse to be really short. But then it gets to a point where, for example, this was 20 nanoseconds. So what we're trying to show here is that you get these coherent oscillations with a starting pulse of 20 nanoseconds. And then even if you make this pulse shorter, you are still able to get the same behavior that you would have otherwise. So you want to have, they are not necessarily important in terms of driving, but they are important if you want to drive something that is coherent or not, if that's what you were trying to do in that sense. Okay. So ideally, you want them to be very short.
Okay, thank you.
So in order to go to these, or to try and start looking at these type of systems, or at least something that is more compatible to these new technologies, or these technologies that we want to interface with, so we started using something called a xenon plasma focused ion beam. And that is because if anybody here has worked experimentally with YIG, which is one of the main things that people are using for cavity magnonics, YIG is not particularly great if you don't have it on a GGG substrate. And that is possibly people have been trying to grow YIG on other things, but that is the best way to grow YIG. If you try to remove the substrate and grow YIG on other things, you have loads of problems. To remove it out of the substrate is quite problematic. So what we were trying to do here with this ion focus beam is you can essentially cut things very nicely. So this is about 1 micron here on the scale bar, and this is a 3-dimensional just piece of something where they just wrote 3-dimensional structures. So we thought, what if we then take just a massive film of GGG and try to cut a piece out of it and then place that on top of a microwave resonator, as opposed to try and grow it. Because, so this work is permalloy, and what you would do here is you grow your resonator, which is on the background here, and then your permalloy film is grown by lift-off. So essentially you put a mask on top, you grow your permalloy, you remove the mask, your permalloy stays. To do this with YIG is terrible. It's almost unaccomplishable, although a few people have accomplished. But it's not a great job. So we thought, would it be easier if we just cut it out of something and put it in a resonator? So what it looked like is something like this. So we took a piece cutting out. So this is a YIG film all cut out with this ion focus beam. And then we take a prism out of it. Then we polish the edges and we get a nice film, and we put on top of a resonator. And these, we had loads of them. So this is a piece of the YIG, and then we cut out the base, and then we put them in various different resonators. And the resonators just, again, very similar to what we had. And for some reason, I don't have a picture here, but we did get actually very nice coupling, and I don't know why I have magically removed the picture, but it is here. So we get very nice coupling, and we can fit them really nicely to the regular theories. The only problem here, which you also find if you have a look at this, is not actually as great as you would get if you grow GGG, because you introduce a lot of losses by polishing and cutting the edges, but it's still very good. So that is where we are sort of going with looking, and this is all at millikelvin temperatures as well. So this is our efforts towards going to these more interfaceable technologies than all of the things that I was talking about earlier. So I think this is me. So just a very short summary there. We can tune these things by just using these external cavity tones, and the field configurable is really an important part to predict or determine the coupling, which is somewhat neglected for a while, but it's quite good. This perturbation theory is a very good way to understand this if you are working in the classical regime. All of the polarization stuff, because we were interested in more quantum behavior that is not using perturbation. But yes, this is where we are. Thank you very much for listening.
Questions, Bill?
Thanks. Have you thought about introducing a third drive on a third degenerate mode in order to get a full, full rotation, degrees of freedom of whatever direction of the transverse field you want at the location of your sphere? Do you know what I mean? So you've got control in a plane right now. So you've got two linear polarizations. One is in one direction, another is in an orthogonal direction. Yeah. If you had a third orthogonal direction, then you could control the direction of the transverse field as well.
So, no, we have not thought about that. But that cavity that I said you had a ring around the sample, I believe that is happening there. So this is one of the reasons why this was an interesting systems, and people are still looking at this. Because this ring, you can control the direction. So we try to make it as flat as possible so that the field is perpendicular in this direction. And then you have the field from the cavity, which is in this direction. And then the magnetic field is applied along a third perpendicular direction, right? But this is quite difficult to control, but also you can rotate in any direction you want.
Yeah.
The problem is it's not uniform, that field, so there is all sorts of problems associated with it. But no, that's a very interesting system. We hadn't really thought of it as something to do. But back to your earlier question, the problem with all of these systems is how to make it so that all modes are truly degenerate. Because even if the samples that we used here were quite small, but if they were slightly bigger, then you get the modes coupling different and they are not degenerate.
Sure.
So, but yeah, that's No, we haven't thought of that. I think that's the short answer, but it's really
Have you talked to people who are trying to measure G-tensors in other materials? Because getting the sign of the different components of the G-tensor can be difficult unless you have access to polarized excitation.
Yeah, no, I haven't actually. So,
Okay. Okay, thanks.
Thank you.
Christina first, then Dennis.
So the state of the art in the quantum limit to couple a single spin to cavity was using, I think you briefly mentioned, like resonators with reduced dimensionality, so very small resonators. Is like what you are suggesting today with controlling polarization can be, have you thought about combining, you know, this idea in smaller cavities, or what is there like limitation?
So the issues that we have found, so we have tried to do this not in these very small systems, but to do in a reduced dimensionality in that the system was a two-dimensional resonator, and then see if we could scale that down. And the problem is when you have these open systems, you have a lot of losses now that are in, if you have a microwave copper box, then the losses, if you all you have is your couplers that are going in. So there's very small losses. So you can have these degenerate modes, and then the coupling or the polarization remains. But then the minute that you make a two-dimensional system, then you just have a truly open systems. The losses from your cavity are much bigger. So it's quite difficult to make the polarization state remains once you put the magnetic sample in. But yeah, that is certainly something that, especially because we were looking at this for a single, for a linearly polarized system. So looking at it for a circularly polarized would certainly be interesting, but it's quite difficult to make.
Hello, thank you very much for a nice talk. My question is a little bit related to Christina's. So were you able to, or are you able to, realize the emergency of exceptional points in your system? And well, in any case, are they like advantageous to manipulate and try to like achieve everything you're kind of like intending to do?
So I think this is, I think a point that we heard earlier of the definition of exceptional points and some of these things. So I would say yes, but there might be people who disagree. So if you're talking about exceptional points in cavity magnonics as level attraction, which is where instead of having the behavior that we've seen here, you have the opposite, then we can. I don't believe the mechanism is the same, and we have been working quite a lot on trying to understand what the mechanisms there are. But there is, to me, and I think it would be interesting to hear people's thoughts on this. I don't know whether what, for example, we see or other people see are truly exceptional points or just interference. Because, for example, what we have here, I don't know if I have an additional slide, but so this is something, so this is the same behavior that we have, but with a sample, as I said, of a larger sample. So you don't have the same degree of polarization, especially here. You only get one of these modes because you now don't have the degenerate modes that you were coupling with. If you look at the spectrum for this, which I don't have here, they look very similar to what you would expect of level attraction, and that have been called exceptional points because you have meeting of two modes at the center, or splitting, or sorry, repulsion of two modes, etc. But for us, we're pretty certain that what's happening here is a problem on how we measure this. Because if we decrease the ratio between the polarization states, then it works fine because we're measuring back some amplitude which is smaller than the amplitude that we put in. But if we put, for example, an amplifier in the path and the amplitude that comes back, which would be higher than 1, is higher than the amplitude that we put in, we get these things that look like level attraction, but it's because our system is saturated and we actually have something that is just the actual VNA doesn't understand what the measurement is, and there's just interference between various systems. So we are doing a lot of work to try and understand that, but there are other systems which we have that we're pretty convinced that we can get that sort of behavior. But yeah, I find quite difficult to discern between what is actually special in experimental work, what is just an artifact of interference, and what is exceptional points in level attraction. So if anybody has insight on that, I'd love to hear. Hello.
Hey, thank you for a nice talk. My question is just a curiosity related to the fabrication using the Xenon FIB.
Yep.
I would like to know if you can comment about the quality of the interface of the lamellas, and if it's possible to avoid implantation compared to the gallium FIB, or doesn't matter?
Yeah, so we weren't really interested in looking at the interfaces from a point of view of roughness. We knew that it wouldn't be great, and we just looked at it in terms of coupling, for example, and damping that is introduced to the system that we just quantify as, you know, a single damping, is much stronger than, is much larger than the regular damping that you would have on a single YIG film by an order of magnitude or over that. So we know that those edges are significantly affected by it. We just didn't really quantify that. In terms of implantation, it's much better than the gallium fib, but again, was something that we just thrown into, is introducing damp into the system. We are not interested in the growth, but it is much better, the xenon fib, in terms of implantation in that sense. But yeah.
Thank you, Ingrid. I'm just trying to, say the names so you get used to, people
Thank
around.
you.
Yes. Did you raise your hand? No.
Maybe just have another quick question. So you showed the two inputs cavity
Yep.
results. I mean, I understand that, but did you have the same or similar platform using stripline? You could have the same, let's say, way to play with the polarization with a stripline?
So do you mean on just a
Yeah.
plane system?
Yeah.
So it's essentially, I think some other people have done this as well. They just weren't particularly interested in polarization. But if you have essentially just a cross, that's the simplest way to
Okay.
realize it. If you have a
Okay.
cross system of strip lines, and then one will have a field in a particular direction, the other one in the other direction, you should be able to get polarization control as well. There are better ways to get it, but yeah.
Because I don't know, maybe the strip line will give like more little.
No, I think so. That's
or-
related to the
Okay.
sort of what I was saying here before. You actually get more losses. So I think it's better to control to make it more degenerate in terms of frequency, but the losses are much higher
Yeah. it's true.
because you have an open system.
Yeah.
So yeah.
Thank you.
But it is something that we are still trying to optimize.
Any other question? Okay, so can you elaborate on this? And since I guess there are a couple of questions about the Rabi
Yep.
kind of oscillation, can you elaborate on the analogy? Because of course, when I think of Rabi, and I'm asking you this because then I want to ask a second question about that. So we have a spin and we just shake it laterally. That gives us the usual Rabi. It's in every textbook. What is the analogy with this kind of picture where you have the chevron-like pattern that you showed us? What is the...
So I think the analogy in my head is still the same, except your spins are not flipping, right? Because that's what you would get when your Rabi oscillation is you're changing the probability from 0 to 1, right? Whereas here, you don't have that because your spin is not actually rotating everywhere, it's just processing. And then you were either, because you're ringing the cavity on and off essentially, so you're driving a knot kind of thing. So you have magnetization that is moving and then back and moving and back very quickly. That's what I think of in my head, to be fair. I don't know if that's particularly accurate.
Okay, so here's my question. So I'm used to, I was recently in Basel and I was involved in some work where we studied Rabi oscillations, chevron type, patterns like that. But in addition to the lateral usual driving, right, the transverse driving, We also had, because this is back to Bill's question related to the G tensors in this system. So you may, and also the spin-orbital interaction, you may have another type of drive, which is we call it longitudinal drive, which basically changes the qubit frequency. So it's longitudinal, so it's shaking like that, and at the same time like that. Encouraged by your talk, I may even talk about this later this week, because it may be interesting to see analogies. And so my question is, in that case where we have both the phase driving and in the usual Rabi drive, it's possible to suppress the main Rabi oscillation peak, and you get side bands, basically. So I wonder whether in this kind of system you're interested in, there would be such a thing as this longitudinal driving.
So I guess the answer is I don't know, but I think one of the things that we were interested in from that point of view is if you have a higher amplitude. Because to me, if you had something that is not quite in the plane or perpendicular to the magnetic field that is set in the magnetization, if that out-of-plane component is not particularly strong, then you still would have your magnetization would just process with respect to whatever is on the plane perpendicular to the field, right? Is what I would think.
But do you have different, because in this case I mentioned the usual Rabi frequencies is, say, at gigahertz, and the phase driving is at the megahertz. So they can do this with a all-wave generator or whatever with two different frequencies. So here you can also have control on that, because that's crucial to suppress one component and get side bands.
Yeah. So we should be able to control it. As I said, I would have just assumed that out-of-plane component wouldn't be too important in a magnetic system unless the amplitude is quite high. I could be wrong. It would be interesting to think about this a bit more. As I said, is immediately I would think if you're all linear, your magnetic field is set in the magnetization, that out-of-plane component wouldn't matter too much. But I would love to be wrong, and I would love to think about it a bit more, because as I said, it's just my immediate intuition, which is often very wrong. So, yes.
Okay, great. Thank you. Fabrizio, just wait for the microphone. They are recording that, so that's why they need the microphone.
It's still about Egg's question, but I think this analogy with Rabi oscillations, maybe there are some limitations with that, because Rabi is basically a quantum phenomenon, and you have all the coherence aspects of the dynamics. Here, as far as I understood, it's more like a semi-classical or classical description. So actually, I think you have a big difference between these two dynamics.
So do you agree with him?
Yes.
Because that was my other question, but I didn't ask. What the quantum part of it?
Yes.
Right? Because at some point at nano plus quantum, and we had Michael pointing out what quantum was or not, what was not. So what do you think about that?
So here is very much, to me, is never, as I said, what we were interested in, especially with explaining this, was actually going the opposite direction and to say most of this is not. But then when you actually, in terms of the coupling itself, even the Rabi oscillations, if you have a macroscopic sample, if you are in a microwave resonator, the quantum thing for us is how you could use, especially, well, if you're at millikelvin temperature and you can work with single photons, single magnons, then you have interactions there that would, well, we would consider quantum there. But interfacing is more interfacing with the angle that we are in. This for quantum is interfacing with quantum technologies, but the actual phenomena, which is why in this I do agree that the Rabi oscillations, which is why I would think if you get any response out of a field that is out of plane you would have to be quite high amplitude, because then you would have precession in the nonlinear regime, which is something quite interesting to think about, but might be quite different to this. But yeah, so that's where I think we sit at the interface of, or trying to interface with, as opposed to the actual phenomena.
Okay. Jean. See, I'm getting better. I'm training my brain as well.
Thank you. So you showed previously one of those slides, like there was a dispersion relation, so you had like phonon and the magnon. So the phonon was up and the magnon interaction was down, something like this. And then you could like shift the gap between them by just I think was changing the size of something, or it was the magnetic field. So by changing the magnetic field, you just shift the gap. So could you also do the opposite of it? Instead of like increasing it, you could like mask, make both mixed up?
I'm not entirely sure where. If you could point to me.
Yeah, I will. Yeah, this one. Yeah. So from C to E, you showed that you can like reduce this gap.
Yes.
But could you also like go more than that, instead of just reducing it, making, for example, the upper branch to go below and then interact somehow?
No, so I don't think so. Here, all that this is essentially what we were doing or saying was showing the validity of this, but which essentially boils down to the fact that here are amplitude terms. So this essentially is the field at the sample position and the field or from the cavity, or the energy ratio between those two things. So if you decrease one of them, then you decrease the coupling. If you increase the other, you increase the coupling. And that is all that this will do, because you don't have, it's a purely linear behavior of increasing, decreasing the amplitude of the drive to the magnetization.
Okay. And also, why do you need to change this Y is related? Is it related to the thickness of the film? Because you change the field, but you also change like just in the right bottom of your every picture. There is like
This
Y.
one?
Yeah. So this one
this is the
15.
position. I think the Y is just the position of the sample. So it's just indicating where you are.
Okay.
Sorry.
Okay. Thank you.
So, by the way, we are already in this discussion period, right? We may as well end and then continue on, but I actually would not let you off the hook yet. I want to elaborate on this point, especially on the point that Fabrizio mentioned, right?
Yep.
Because we usually don't think about this too much when we think about what is quantum and what is not quantum. It's like when people say, is Anderson localization quantum? And, I used to think that, but then when you think about it, classical waves can localize in random media, and there are many papers written on that.
Yep.
So I'm just wondering now, what is really quantum about this Rabi, right? I mean, the question is, it seems to me you draw pictures where you look like you have something which is a spin, or, like a spin, and then you can shake this any way you want, transversally, longitudinally. So Fabrizio, why do you think it's not really quantum in the ordinary sense of quantum, right? Because of course, for the usual Rabi, any quantum mechanics textbook, it's a Schrödinger equation for two-level system coupled. Then you do the simple algebra. It's all analytical. You get the oscillations there. And also with this generalization that we had with the transverse drive, with the longitudinal drive, it's the same story. Simple algebra. I'm going to show you later this week. So, would you like to elaborate? So I'm provoking now the audience. You can use the board if you want to.
Okay. Yeah. When I mentioned that, I was thinking basically on density matrix. Okay, because if you calculate the quantum evolution of a system. Hello? Okay? Yeah. Loud. Okay. When you calculate the quantum dynamics of two-level system, like this one, for instance, you have the density matrix. You can calculate that using von Neumann equation. And when you look all the components of your density matrix, I mean all the elements of your density matrix, you get off-diagonal elements. So, and this results in purity equal 1 all the time in the dynamics, unless you have some dephasing the coherency mechanisms on that, right? So I think here you are more in the classical side. If you can calculate density matrix for this system, probably you will get some diagonal density matrix with 0 elsewhere. So you have basically a classical probability distribution instead of quantum. I mean, and if you calculate the purity, you get less than 1, I guess. So I'm talking in this sense. I don't know if I'm clear here.
Thank you, Fabrizio. So Michael has some comments.
Yeah. I'd like, I think all these points are really good points, and certainly you're correct that if you do the calculation quantum mechanically and semi-classically or classically, you actually get the same answer. So then the question becomes, there's a very narrow distinction between something that cannot be distinguished as to whether it's quantum or classical and something that is classical and not quantum. So, you know, in principle, there is a series of measurements you can do on the spin 1/2 object that would tell you that it's a quantum mechanical object. But the Rabi oscillation that you're talking about there won't tell you that because, as you say, you will get the polarization as a function of time. It will look like a classical object. This is a well-known special feature of the spin 1/2. If you do have the spin 1, though, then you can construct some internal degrees of freedom that will, in principle, be able to tell you that it's quantum mechanical rather than classical. But it's just a peculiarity, I think, of the spin 1/2 object in the ensemble of the spin 1/2 object versus the spin 1 and higher.
Okay, Bill now.
I think people are saying more or less the same thing, but I'll just sort of repeat it in my own language so people who know my language can understand. So I think there's a big distinction between vacuum Rabi oscillations and purely driven Rabi oscillations with a classical field. So, of course, vacuum Rabi oscillations, where you would start, say, with a single excitation in your magnetic system and no excitation in your cavity, will evolve into a pure state of the joint system that will have entanglement at some intermediate time. And then this can be reflected in the reduction in purity of one of those subsystems. And so you cannot describe this classically. And there's a measurement that you could do on the joint system, for instance, that can clearly distinguish from any classical evolution, even for a spin 1/2. But of course, if you have a spin 1, you can just do your measurements on that spin. Yeah. Right.
Because it's an interesting discussion. Where is the other microphone?
Yeah, I totally agree. I mean, I think the question also is whether you're talking about one excitation, as you were, or a large number of them. And in this particular case, I think you have a very mixed state that you're working with, and you're watching the evolution of many, many numbers going to those numbers plus 1, and then coming back to those numbers again. And there you would be unable to tell the entanglement of the system by probing it. You really do need to get to that single quantum limit, and then you have the ability to see it. So I think we're all agreeing. It's nice to sharpen the precise things.
Just to formulate a bit more the problem, I think that if you keep measure only the z component of your spin up and down and look at the population, you will not be able to distinguish if it's classical or quantum.
Well,
if you measure only that.
If there are a lot of them. If there is one, there'd be, it depends on the statistics, right?
Yeah, But the
Because if it were
statistics
classical, you could get a number intermediate,
the
which you can't
statistics will
quantum.
give you the same thing. So to distinguish if it's quantum mechanical or not, you have to rotate the basis. You have to start measuring in Y and X direction as well.
Well, no, if you had
And
a single
perform some
spin,
tomography.
if you had a single spin and you measured along a particular axis, you would get one of two possible outcomes, and that would tell you it's quantum mechanical. Whereas in the classical situation, you can get an intermediate value for the
But
spin pull.
in the end of the day, you will find some population distribution.
No,
right?
single shot.
Some statistics.
So single shot measurement.
Yeah.
Yeah. So I think one of the things here, well, somewhat different to the discussions, which I am very in agreement with, but to your question of what is quantum or not, and I think back to your first point, in the systems, I would be more conservative in saying that, you know, the Rabi oscillations and everything is a magnetization that is processing, so it's all classical to me. But if you think about the example that someone was asking about, level attraction and exceptional points, which people have said we can see this in the systems in different cases. If you look at the, if your definition is the sort of you're looking at the matrix, whether you can diagnose it or not, I don't think that is true here, but I would still think that the phenomenon is classical, intuitively. So I think it's quite a mixed, I don't know, I think it depends on who you ask. It really does.
So I think also there's an element of experimental humility, which I very much respect, which is if you can't prove that it is quantum, you're not going to say that it is quantum necessarily. It may be quantum. You just may not be doing the experiment to tell that it's a quantum system.
It could be. Yes, I'd agree.
And that's the tricky thing when the quantum system and the classical system behave the same way for the particular experiment that you're doing.
Yeah.
That is one quantity, but you do not need an H bar for an entanglement measurement, right? I mean, you H bar is only a dynamical thing. I can prepare two objects in an entangled state without any H bar involved in it, whatever, and then I can make a measurement of it in it. And from that, in principle, I can tell whether the system is entangled or not entangled without any H bar, without any propagation, just in a thought experiment. So I don't need H bar.
Oh,
But we can also let the speaker sit down and then we can continue discussion.
thank you.